Well, I don't have methods. I maybe have a method because I've kind of just narrowed it down. You know, like why? I mean, we measure other things, but you know, some things you do just because you know your colleagues say you should. You know, but some things are just more important. I'm pretty excited about the research, partly because it was never really intentional. So you remember back to your graduate years. Okay, you're in your graduate years, right? Graduate study years. Probably you know, your advisor is not always correct. Right?
Maybe.
maybe not. Okay. You're actually a new faculty member, so you don't. I went against the advice of my advisor in this research, and it actually led to something. So that's you know, sometimes you have to explore. Okay. So I don't really necessarily have to go over this, but you know, the idea, of course, the problem is that we need food production. We need to feed the people, the plants, and the problem is focused on nitrogen here. It costs something, it requires energy, and it releases greenhouse gases and pollutes the water in excess. You know, it's a real dilemma. So I'm not sure if I have a simple slide. I didn't have I tell producers that I'm working with that, you know, we've studied nitrogen for more than a century. I mean, our colleagues have been there, and yet it seems pretty simple that we, you know, should be able to predict how much nitrogen to be applied. But yet we have all of these eutrophication problems. We know that nitrogen is being lost. Our world is somewhat nitrogen saturated because of the availability, you know, kind of the low cost availability of nitrogen. And that's not necessarily a good thing because, you know, we have to deal with it then afterwards. Well, the practical thing is, I was at a soil health training event in Virginia, Eastern Shore, last week, and I asked the audience, you know, what they saw in this. So maybe I can ask you what you see in this graphic, you know, just as a way for you to feel comfortable engaging me in this presentation. What do you
Your productivity of nitrogen decreases actually as you apply more.
That's right. It's not a linear relationship. Right? What else do you see?
The law of diminishing returns.
Well, that occurs. That's right. Hunter, you got to answer.
Well, on the other end, you don't put any nitrogen on, you don't have any yield.
There you go. Yeah, that's a big one, right? It's true. But so I'm going to get to that point in a moment. But the available nitrogen, this part here, it's important how we characterize that. Traditionally, it's you know, just basically, you know, you sling out some fertilizer and that's the available nitrogen. How much nitrogen fertilizer do you apply? And that's the response. But in fact, in the field, you're always likely to get some yield. Soils have an inherent capacity to produce something, right? And so that's kind of the basis of where we're going with the research. But I wanted to just bring, you know, unfortunately, I don't know if you're familiar. I know some of you are familiar with English units, and maybe some are less familiar. And I've been using this presentation for producers as well, and so I put it in English units to accommodate their needs. But if you assume 200 bushel an acre corn, there's a certain amount of nitrogen that just you know that it's going to need. It's going to need approximately 1.5% nitrogen in the grain and then 1% in the stover. That can vary, but the total nitrogen need is 280 pounds of nitrogen. So it's a matter of where that nitrogen comes from. So that actually comes to a ratio of 1.4 pounds of nitrogen per bushel of grain. 280 divided by 200. So that is a number that some states use. They recommend 1.4 pounds of nitrogen per bushel of grain. And so they basically, to avoid any limitation, they say, well, that's the amount of fertilizer you should apply. Whereas we know that there's something that the soil can provide. So in North Carolina, we've done some sampling, and we found that there was roughly 57 pounds of nitrogen per acre in the inorganic form. So that can be partly ammonium and partly nitrate. Mostly the variation occurs in the nitrate rather than the ammonium, although we've had some samples that were from manured, animal manure systems, and so the ammonium level can be a little bit higher. But so that level of, say, roughly 60 pounds per acre is not trivial. It's some amount, but it's also a relatively low amount. So it's not the 280 pounds that is needed. And then most people would assume that the difference has to be applied by inorganic fertilizer. So I believe most states don't measure inorganic nitrogen. I'm not sure in California if the soil testing facilities, is there a state soil testing facility? Or is there private owned? Private owned. And they probably don't measure nitrate necessarily.
They do.
They do? Okay, and they report it? Okay, all right. So other states, they can measure it and they will measure it, but they don't really report it because they don't want to confuse the producer. Because they're not going to make a recommendation on it. But if in fact we want to be resource efficient, we should know how much is there because some fields have 150, 200 pounds of nitrogen in the nitrate form already in the field. So why would you apply when you don't need it? Okay, so that would be important. But there's this organic nitrogen supply that is potentially very large. Now it's very large in these samples, and there's a large variation because we have a number of different soil types in North Carolina, and also different management systems. But there's more than 4,000 pounds on average of organic nitrogen. But now we know that that's not really available, but there's potentially some of it available. A lot of the older literature would say that 2% could be available. So that might be 90 pounds per acre, right? So it could supply something. 90 plus 60, that's 150, let's say. And so we got about half of the nitrogen that is needed. So that could produce half of a corn crop, perhaps. And producers don't want to produce half a corn crop. They want to produce more than that, right? They want to have what's so this thing I can go through very quickly because probably you know most of this, but the focus, I put the focus initially on fertilizer, that's where we kind of put it, but there's this surface soil inorganic nitrogen, and we should measure deep profile inorganic nitrogen sometimes. I mean, in some conditions, especially in drier conditions, it would be available, and we should measure that, but it's not an easy task to measure. So you have to core and you have to get a representative sample. The idea, though, is that there's mineralizable nitrogen in the organic fraction, and then there are various loss mechanisms, various inputs that are out there, and then these constraints to why mineralizable nitrogen could be available or not. So it becomes, it should be simple, but it's complex. There are a lot of variables out there, and that's why, even after 100 years of research, we don't have a real good system, let's say. So I don't have to go over this much other than to show you that on the biological activity that I'm measuring, we're kind of isolating the periphery. All of these organisms could be potentially important, but we dry the sample, and so we're excluding them. Other than if they were in the sample, they're dead and they become food for the other organisms, right? But they're not participating in the activity that we're going to measure. We're focusing on the microorganisms alone, the bacteria, fungi, and actinomycetes, as well as any organic material that's in there, of course. So this just, surface residues are important, roots are important. Microorganisms need certain things, this is just basic information. And essentially they need carbon sources, right? They're heterotrophic organisms, they need the carbon sources to consume, and they have to have some access to those nutrients. So our scheme in our laboratory is focused on this picture here, in that we measure total organic carbon, we measure the particulate organic carbon, which is a physically defined fraction. It's dispersing the soil and then retaining that carbon on sand-sized material, the inorganic and the organic particles that are on that physical fraction. We use fumigation incubation without subtraction or control. We're probably the only lab in the country, maybe in the world, that uses this methodology that was originally proposed by Professor Jenkinson. But the fumigation extraction method is almost always used. Now, Christina, you use this? Right, and almost everybody I talk to, so why do you use it?
Is it simple?
It's simple, it's relatively simple, and it's rapid, right? I think that's really the only reason, right? That anyone would use fumigation extraction, and it may be useful in some cases. I'm a little bit jaded. We've done some work on it. Fumigation incubation relies on the organisms to reconsume that. Whereas the fumigation extraction is again a chemical extraction. We rely a lot on extraction. Chemistry is kind of like our mode of operation. Well, it can be useful, but it has limitations, let's say. So and then we also measure this mineralizable fraction, and then we do the short-term part, and we do a 24-day mineralization. So I wanted to make the point that carbon and nitrogen are related, but in the short term, it's really complex. In that, it's understandable that if you add residues, carbon source, you have this high microbial activity. You may lead to net immobilization, but with time, almost all residues that have any sort of nitrogen in them will mineralize eventually. The amount is quantifiable, and it's variable, and that time period is variable. But it just is a matter of time. So the immediate reaction is that it could be immobilized, and that's a negative thing. In the field, if you have residues that you apply and that the crop doesn't have access to nitrogen, then you can't really take credit for it. You have to wait for that. All right. So, but in the long term, I wanted to go here. We measured over, say, a 10. This is actually from 12-year period that we've measured the carbon accumulation versus the nitrogen accumulation. And there's this steady relationship. And if you're, let's see, I don't have the equation on there, but that relationship, there's basically a tenth of the carbon is sequestered as nitrogen. So that means there's a 10-to-1 relationship. It actually was 10.1, I believe, really close to 10, which is stable organic matter. That if we accumulate carbon, we're going to accumulate nitrogen. It's gonna draw the nitrogen, any excess nitrogen at some point is gonna have to feed the carbon accumulation. It's the organisms sequestering it into organic matter. And then it doesn't necessarily become available to the plants right away, but in the long term, it is available. And this is a process of more of a long-term view that we are building the organic pool that will serve us in the future rather than immediately. Too often we focus on the immediacy of, say crop residue decomposition. What does it provide this year? Well, be patient. Over time, producers are out there for generations. It's not that they need to have answers all the time right away. For us as researchers, we want to have the answers right away, right? We have to publish. But it's a matter of, it's a different way of thinking that we should be building the soil rather than tearing it down. So most farms are in some sort of steady state condition, and that's where we want to get to. Now this graph is simply to illustrate that we had 3 different crops, and that the crops in their carbon mineralization potential, the soils, they reacted very similarly, in that there was a difference between no tillage and conventional tillage. This was after 10 years of no tillage in this comparison, and that the nitrogen reacted somewhat similarly. It was a little bit different dynamic, and but so it gave us the view back some 25 years ago that okay, why if we're interested in nitrogen mineralization, could we not predict this with carbon mineralization? Because there's potentially that long-term steady state relationship. It's complicated, of course, with the immobilization, but could we use this? And so that was the basis. And actually, when I said fumigation incubation, that's what we were after. We were after how do we define this, these dots on here were to say, well, do we subtract a control or not, and could we do this? So we started with dried soil, and this was not necessarily a preferred way, but we did it, and we were focused on defining microbial biomass. But what we found was that if we started with a dry soil, we had a soil that is relatively low in activity. It proceeds along, and that becomes this line here. This is the inverse relationship here. This is the daily mineralization that occurs. So you get a higher mineralization in the beginning because of this flush of CO2. You dry the soil, and re-wet it, it has a higher activity. But the key was that none of these lines interacted. None of them crossed over. There was this common description that could be made. Now, it doesn't always occur, I suppose. I can't say that with 100% certainty, but for the most part, those lines don't interact. Once they're low, they stay low. Once they're high, they stay high. So that was the impetus for then defining. I was interested in defining this mineralization at steady state. So we knew that we dried the soil, and we had to overcome that, okay? So we had to kind of remove this data. These data were removed, and my tutor, my major professor said, okay, if you're gonna do that, then just don't even measure this. Well, fortunately, I measured it, because this rate of mineralization initially relates very well to this rate of mineralization later on. And this is a simple description, and it shows the same kind of information, that the curves don't interact, and that the depth of sampling is very important. So the surface is oftentimes much greater in microbial activity than lower in depth. And I was interested in this basal respiration, but we have this flush of activity that occurs. So this flush of activity then was used because we were interested in this linear rate of mineralization, or this near linear rate of mineralization, but the flush was already predicted. It was not necessarily, we could use a coefficient of some sort, a mathematical coefficient. But that wasn't the point, I think, that I was interested in. I saw separation, statistical separation right away, even after 3 days. So this then led to the idea that maybe we could use the dried soil, re-wet it for 3 days. So in total, it probably is a week-long assay. You have to dry the sample. It takes some time. You have to then incubate it and get the analysis. So it could be used as a soil test. And so I made some argument that we could use this as a soil test. Solvita has, my colleague Rick Haney, he went to school with me at Texas A&M, and he was more interested in this. I was interested in, so I work for the USDA, and so I had a different kind of emphasis, and I was working on that, but I always measured this mineralization. And over time, I had to come back to it because Rick developed this with Solvita. So Will Britton is the president of the company. And he did this, I believe, for a compost application, to understand whether compost was mature or not. And so anyway, this is so their test is to put soil in a container. They put the water, they drill some holes in a plastic beaker. The water is in this glass vessel, it absorbs it, and then it becomes somewhat saturated. And in some soils it's saturated, and others it's near field capacity. This paddle here is a color paddle. It absorbs the CO2 and it changes color based on the amount of CO2 that's involved. So their test is for 1 day. Now I want to go back to this here I'm a little bit concerned yet about 1 day, because if we take it to 1 day, it's like over here. Is there good separation? That would be my argument, is can you really, I think it can work, but the longer one goes, the better. You get better separation, more statistical separation, let's say. And we also use more soil. We use a different wetting method, so there are some differences. I bring up this point here. This is a little bit complicated, but we had 5 sites where some ARS colleagues got together. I wanted to bring this up because the flush of CO2 is what I measure in 3 days. We measured in 24 days. We measure the microbial biomass through the fumigation incubation method. This is permanganate oxidizable carbon, and this is protein measurement that is promoted by Cornell Soil Health. This is the treatment F value. So all of these sites had roughly 5 treatments, 3 replications, and we wanted to, so the higher the number, the more robust the test. So the 2 with the highest values were the flush of CO2 and carbon mineralization in 24 days. My point being that it's as robust as some of these that are promoted. I've gone to the Soil Health Institute's meetings, and there are some vocal members that say we have to measure protein. Absolutely, right? And others that say we have to measure permanganate oxidizable carbon. Unfortunately, the discussion around the flush of CO2 has been somewhat heated. Some people like it, and mostly it's farmers, and scientists don't like it because they haven't been explained what it really means. So that's why they have kind of somewhat ignored it, let's say, but I wanted to show that actually the treatment separation was good with the flush of CO2, And if we look at the coefficient of variation, it's equally well as the permanganate oxidizable carbon. So that test is chemical in nature, and it's probably a reasonable test of carbon availability. It certainly works, but it's chemical. It doesn't rely on microbial activity. It just extracts whatever's in the soil based on the chemistry there. So I believe that if we want to measure something as biological activity, we need the biology to participate. Now, I'm not trying to say anything about the characterization of organisms, but mostly we don't necessarily, if we want to know the characterization of organisms, we use a physiological profile of some sort, right? Or DNA profile. And that's what we have to do if we want to know who participates. In this test, it's the community that's participating, and we're not necessarily trying to discern who's participating. So combining it with characterization of who's participating, this could be really valuable. So there are some key considerations that I've outlined, is that first of all, you need to get a good sample. There are some people, send in samples that there's basically, it's mud. We don't know exactly how it was sampled. I try to tell people I'm after 0 to 4 inch depth samples. If you use 0 to 6 inch as your depth of reference, then it has to be 0 to 6. It can't be, well, it was too hard. I only took 0 to 4 inches. It's like, well, because the depth matters, right? It matters a lot, at least in the southeastern U.S. So you have to get a good sample. You have to have a defined soil depth. We dry the sample to a kind of a common protocol. We use 55 degrees C for 3 days. Whether it's dry or wet, we do it for 3 days. We sieve our soil coarsely to less than 4.75. This is probably one of the least favorite things that the students in the laboratory like. It's like sieving the soil. It seems like like a really easy job, and it is a pretty easy job. But it's actually when you try to sieve it coarsely to less than 4.7. I told them I don't want pulverized soil. I want to have it just past the 4.75. We're trying to retain some of the physical aggregation of the soil. And because we know that if we pulverize it, we sometimes get a larger burst of activity, and sometimes we get inhibition. It depends on the moisture relationship there, once we wet it. So we wet to 50% water-filled pore space, and I can maybe describe that a little bit later. And we use an alkali trap and base or acid titration. It's kind of laborious. You can use an infrared gas analyzer. It's very possible. Others use the paddle, the colored paddle by Salvita. You can use, I forget the terminology. Cornell Soil Health, they use actually electrical conductivity. They stir the solution, right? I think it's electrical conductivity measurement. All right, so this flush of CO2 in 3 days is highly related to the basal soil respiration. This happens to be from only one soil type, but from different depths and management systems. But it's really strong in that the 3-day value correlates, in this case, to what the daily rate is from 10 to 24 days. So in most of the time, the value at 10 days is now starting to be very linear. So we use 10 to 24 days for that. We could actually use a mathematical expression and use that too, but it comes out very similar to this. So it relates to steady state microbial activity. Even in soils taken from 3 very different regions, the Kansas soil is a mollisol, Georgia is an altisol, Michigan an alpha sol, we get a relatively stable relationship between the flush of CO2 and microbial biomass carbon as determined by the fumigation incubation method. There are some differences there, but in general, it's relatively stable. And then we have this relationship between flush of CO2 and nitrogen mineralization. And that's where I'm really trying to take this, is that we, for practical purposes, farmers will be really interested in knowing how much the soil can provide. Because if they can apply 30 pounds of nitrogen, or they're being told to apply 130 pounds of nitrogen, it means something to them. As long as they're certain that they're not going to lose out on yield, because there's a cost of applying more nitrogen, right? And so they have to recoup that cost. It's an investment they have to get a return on. And fertilizer is not real expensive right now again, but it is not going to be cheap in the future. I mean, I can almost bet on it. And so it's, and also ecologically, it's doing a lot of damage to our environment. So we need to pay more attention to it. So the idea here is that we had 61 different fields in North Carolina. The graduate student, Molly Pershing, she thought the literature said that the literature says soil texture matters on nitrogen mineralization. It does. Soils of different texture have different nitrogen mineralization potential. But the key that we were looking at is the relationship between this possible soil test and nitrogen mineralization. Not the absolute amount of nitrogen mineralization, the relationship. If we add soils with less clay content than the first set, there's essentially no difference in the relationship. And across even less clay content, there's no relationship. Now, it's not a perfect relationship, but 63% of that variation was explained by the flushes here too. So it's certainly not perfect, but it is there's a lot of variation with this estimate here. Let me just say, in 24 days, we have to estimate nitrate, ammonium, at the beginning and at the end of 24 days, so there's multiplicative and additive errors associated with this. So it's not easy, and also some of those values that are very low, you know, it can be a large error associated with that. So I think we've got a stable relationship. It's independent of soil texture. So we basically have this relationship. Now, Hunter, I told you 20%, but here this coefficient here says 26%. So you know, there is some variation on different data sets. Okay, so again, going back to this curve here. So this curve, this available nitrogen is really composed of some components which we should be able to characterize better. We should be able to measure surface soil inorganic nitrogen. We could measure residual in the profile. We definitely can measure long-term stable because we can actually, you know, determine total nitrogen, you know, with a combustion instrument, no problem. But it's how do we get at that biological activity? So I think that's where we're leading with this research is we're characterizing that fraction right there. The reason is that there are economics associated. If we know that there are sites with a high available or high fertilizer response and low nitrogen availability, we can increase their profitability. Farmers want to hear this. They want to know that yes, we're doing the right thing. But they also want to know that if they're already saturated, they don't have to apply additional fertilizer. The last couple of years have been really revealing to me. I've worked with Virginia Department of Conservation and Recreation. They are the Soil and Water Conservation Division. And they have producers, they're like, you really didn't have to apply citrus fertilizer? I mean, they were like, well, but we always do. I mean, we have to, right? We were told to. They were a little bit surprised when they saw the results. So in the end, though, we want our soils to have this large amount of available nitrogen, but we have to capture it by keeping the soil biologically active, having that carbon there to sponge it up so that it doesn't leak away, either runoff or leaching. We need to keep it in this biologically active form so that when it warms up, or when it becomes wet, in your case, that it will then release it to the plants. And that's the idea, is that we have to, we want to enlarge that pool, but we have to understand it more. Okay, so, all right. So I said in the beginning that actually soils don't just not produce anything, right? We still have some in Virginia. The red ones are what I'm going to focus on from here on out. Those are the sites. So we have, this is the Shenandoah Valley in Virginia. That's the northern Piedmont up there. Then we have the coastal plain region in North Carolina. And we've got the Piedmont region. This is a hilly region, red soils. And then we have one site in the mountain region, which is mountains but river valleys. Okay, so the way we had to calculate nitrogen availability and the amount of nitrogen that should be applied is to look at the cost-return relationship between grain and cost of fertilizer. So we use these three sets of numbers. Whoops, I went too far. Is that I basically chose this low nitrogen and high grain price, this 5 pounds of grain per pound of nitrogen. Some people use it the other way around, so the number becomes 0.08, based on bushels and price of fertilizer. Anyway, we have to achieve 5 pounds of grain for every unit of nitrogen. Otherwise, the nitrogen that is applied is basically, it's just being thrown away. You're not getting a return on your investment. If fertilizer costs something, you have to get at least that amount left. But these other scenarios could be realistic, and they have been in the past, and they could be in the future. But we chose, a very conservative one because we didn't want to, mislead anybody at the beginning. All right, so this I just wanted to show you quickly the kind of response that we got. I did take out some slides where I showed we had generally 3 unreplicated strips. These were field length strips. They typically were about 600 feet long, and they were at least 12 rows. So the farmer was willing to not have fertilizer on these relatively large strips. Anyway, we hand sampled 12 different areas in there. So they went up and down the hill. So we felt that we were getting variation, and so we had replication, pseudo-replication in this. This is a response where there was, we could calculate what this optimal nitrogen would be. In this case, the highest rate of side-dress fertilizer was 140 pounds of nitrogen. And so at the low threshold level of 5 pounds of grain per bushel per pound of nitrogen, the optimal rate would be the maximum that was applied, 140 pounds of nitrogen per acre. That's for replication number 1. Here's replication number 2. It was also above that threshold, so it's 140 pounds of nitrogen. Here's replication 3, 140 pounds of nitrogen. And replication 4, 140 pounds of nitrogen. But you can see that some of them had curvature, and so the level at the high threshold level was different. All right, so this is the average. The average was that it was 140 pounds of nitrogen per acre. These are the data that actually were assembled across the 36 fields in North Carolina and Virginia. This is the flush of CO2 as our soil test biological activity indicator versus relative corn grain without side-dress nitrogen. So if we didn't apply fertilizer, how much of that compared to the highest rate of nitrogen fertilizer that we could calculate? So there were plenty of fields where we had low relative yield, and they had low flush of CO2. Those fields that had the high biological activity had the highest relative grain yield, so they didn't respond to nitrogen as much. There are 4 squares in there that I've highlighted, and these 2 are 2 drought sites that realistically I can't really keep them in there. And these 2, one of them was an anomaly I can't explain. The farmer couldn't explain to me either. But they kind of balance each other on both sides of that line there. So I've taken them out and added in now the silage site. So the squares now are the silage, but the squares are all up there on that. So Virginia producers that produce silage, they have manure application. They're dairy producers. They have high biological activity. They're applying manure. They're using no-tillage. They're using double cropping. So but these data are field data, and 64% of the variation in the relative corn yield, corn grain or silage, is explained by this simple test of the flush of CO2. It's not perfect, but it follows a general relationship. So I think it gives us a lot of confidence that it has value, that we could use this, because actually if we go back into the literature now who studies phosphorus? Who studies potassium? You? Yeah. Okay. Well, I suspect in the calibrations for these soil tests for phosphorus and potassium, the data probably aren't near as close in a field calibration.
Yeah.
Because I've seen the phosphorus in the literature. I haven't seen the potassium yet, but the phosphorus, there's a large scatter. But it's accepted. We use a soil test and we apply fertilizer based on that soil test. So there's a little bit of a discrepancy on why we could use this versus why we even use a test that it doesn't have a good relationship. So there's a lot of confidence in this relationship here. And I would, so now what I've done is transform those data into the pounds of nitrogen per bushel of grain. Because that's a simple measure that producers really understand. They all tell me, I'm gonna grow 180 bushels of corn. I'm gonna apply 180, but I've applied 60 at planting already. So I'm gonna apply 120 now at citrus. They understand this. They know it. They've been well educated on it. The relationship is not really that good, but it follows a general trend. And the issue is that if we kind of hid these points down here, these are actually not much of a concern really, because these, if you take these points out, we still have this strong relationship. I say that because we would recommend higher fertilizer than maybe the producer needs, but that's not what their concern is. They don't want to lose yield. They are concerned about if I had a need for fertilizer and your soil test said I didn't require it, they would be upset. So we're kind of worried more on that upper end rather than the lower end. Okay, for silage, a similar relationship occurs. I wanted to go back. So the intercept is 1.05. So it kind of relates to what we expect. In a conceptual manner, these data validate the approach that with soils that have low biological activity, 1 pound of nitrogen per bushel of grain is about what they would need, at least in this environment. Maybe in Illinois, it would be different, and that's maybe why a 1.4 might need to be done. But in this condition, 1 works, okay? So I'm gonna get to the other point. And I've been told that for silage, the value that they use is 7 pounds of nitrogen per ton of, no, I'm sorry, it was 8, because the intercept here is 7.2. The value they promote is 8 pounds of nitrogen per ton of silage. So if they wanted to produce 20 tons of silage, and that's a normal yield, then they'd be needing 160 pounds of nitrogen. 8 times the 20. A lot of them want to shoot for 30, right? So they're trying to they'd have to apply 240 pounds of nitrogen. So this relationship also makes sense, and it's relatively good. I mean, it's not perfect, but this becomes now. I'm taking a kind of a leap of faith here, and at this point, I believe that I have justification for making this leap of faith. Is that I've already set up what preliminary would be a soil test biological activity, basically a calibration of a soil test to a recommendation. So now, if you get a cell sample and you have less than 200, let's say in this case less than 180 milligrams of CO2 per kilogram of soil for 3 days, you would need to apply 1 pound of nitrogen per bushel of grain. If in fact you had 500, you would only have to apply 4/10 of a pound of nitrogen per bushel of grain. So if your yield goal was 200, you would be applying, what, 80 pounds of nitrogen. And I haven't, we could maybe go down to 0, but I don't think that it's maybe legitimate for me to go that low. Is that if in fact we get a soil sample that's in the 0 to 4 inch depth, that is 1,000, and we've seen it, it happens, I would still be uncomfortable recommending to a producer that you supply no side dress fertilizer. Because if anything, when the corn is approximately 30 centimeters tall, that's when it needs the nitrogen. If you don't have it, applying something might be still a reasonable strategy. But at least this becomes a filter to say, okay, it's 30 or 40 pounds of nitrogen versus 200. Okay, so that becomes the relationship. We've done this also in wheat. So we've had a number of sites, and it's already time. So I'm just going to quickly go, we've had a number of sites. Actually, my Brazilian sandwich student, PhD sandwich students have been helping me out with that. And so this is one of them here. Anyways, we've had a number of sites. We see a similar type of response. It's not perfect. We don't have, this year we'll be harvesting soon, and we'll have 10 sites to add to this, so we'll kind of double the number of sites. And we've also done it in Tall Fescue. This is Spriti. She's from Nepal. She's on the project. We've had a number of sites here. We've kind of had some inquiries from West Virginia and Georgia, so we went there. And we do see this strong relationship between flushless yields and net nitrogen mineralization. But we also find that we have sometimes some soils just, hey, I don't know, she repeated these and she got the same results. Okay, then maybe there was an immobilization. And we do see this occasion. But for the most part, there was not this immobilization. So that's confusing to me. Anyway, so this is a typical response that we get. Again, here we did 4 applications, 4 rates. We tried to be as thorough as possible. So we get a response sometimes, and this is kind of our extreme response. But so I put this in a little bit different manner. This is the initial response. So if we applied 1 pound or 1 kilogram of nitrogen per hectare, what would be the yield response? So again, the economic threshold is set at 5. 5 kilograms of dry matter per kilogram of nitrogen. Almost all sites are lower than that. Recommendation in North Carolina, in Virginia, in Tennessee, is to apply 60 to 80 pounds of nitrogen to fall stockpile tophet, independent of what soil can provide. These data would say, I don't think so. And so this is from 1 year. We repeated it, and the second year, actually I don't have those data on here, but the second year, we got even fewer responses. Some of them were drought affected. We had a severe drought. But I wanted to point out here that this was 4 replications of 4 rates of small plots in the field, 10 foot by 20 foot plots, so 3 by 6 meters. And we harvested almost that whole entire area. So we were getting good dry matter yield estimates, I believe. But the variation in the yield was much larger than the variation in the flush of CO2. So we're pretty confident in what number we get as the biological activity. We're less confident in actual the yield. Now, these are pastures, they're variable. We understand that, but we do the best we can. So I don't think we can blame any variation in biological activity as a source. It's at least it follows. So this, you've seen this, the working hypothesis is to replace available nitrogen with a test of an indicator. It's not available nitrogen, it's an indicator, and this biological indicator that relates to nitrogen mineralization. This is essentially the test. It's really simple. When I did my PhD, my advisors probably spent $1,000 a year. I was the cheapest graduate student. I'm pretty much still the cheapest researcher. I mean, my graduate students, we do have laboratory analyses, and I'm not trying to make too much fun of it, but the methodology is really simple. You have a canning jar, which you can buy in the grocery store, or you can get it from your relatives that they got them around. I'm telling you, my mother still got them. Anyway, we put soil in. We actually use 2 vessels of soil. So we put 50 grams in each, and these are markings for every 10 milliliters of soil, and so we use that as a volumetric determination, so we kind of get a pretty good idea of volume. And then this is the alkali trap. It's got 10 milliliters of sodium hydroxide. It absorbs the CO2. After a certain period, we cap it. We add barium chloride to precipitate the carbonate, and then we titrate it with an acid and use a color indicator. So the procedure is relatively simple. The biggest expense is the digital burette. When I first started, I used a manual refillable pipette. Burette. I was, yes. Anyway, I did a lot of those, and anyway, I think the keys between Solvita and this is that we use a larger volume of soil. We use 100 grams. They recommend 40. They wet from the bottom. Actually, they've changed. They've seen our results, and they're convinced that they should wet from the top. My colleague Rick Haney still wets from the bottom. And we've looked at this on sandy loam soils. The water is taken up to such a large degree that it completely saturates the soil. So there's not any more oxygen in it. And so it inhibits mineralization. Whereas all the other soils, they tend to kind of come to some agreement that there's balance between water and oxygen. And so we get reasonable values on whether it's from the top or from the bottom. It's easier from the bottom. So ease is not always the best criteria for selecting a methodology. So we use 3 days instead of 10 days. So there's a difference in magnitude of the value. And we use the acid-base titration. So there's a little bit of question about the paddle, the color paddle, whether it really is quantitative. We're testing that out now. Rick uses the infrared gas analyzer, so I'm pretty confident he's getting what he's supposed to be getting. But I'm not sure. So there are some concerns about about storage of soil. I've collected some samples from 25 years ago. I've reanalyzed them, and then if I do a 3-day, I get the same number. The microbes are in waiting. They don't you know, there may be, the community is maybe a little bit different, it's possible. We don't know that. But their activity is the same. Whereas if you stored a sample that long and just did one day, some soils seem to have a lag phase, and so they're not ready to be awakened. And so they need a little bit longer period. So there is a concern about that. I still think one day could work, and we're just going to make the calibration. That's all. I'm sorry, I'm taking your time. So I published this paper, which was February of 2016, and it kind of outlines the whole procedure, gives a little rationale, and I wanted to provoke my colleagues at state soil testing labs. I wanted to say, you know, why aren't you doing this? It's related to something that's important. Producers are interested. Citizens are interested whether their water is being polluted or not. Why don't we do this? And the reaction hasn't been necessarily strong. It has, as long as you give a good argument, I think all of us are reasonable people, and so it has some value. So where I'm taking this is that I want to influence our own state Department of Agriculture, how they measure and recommend nitrogen. This has to be published, obviously. Department of Conservation and Recreation in Virginia, they're waiting. They're in the Chesapeake Bay. They have a real strong interest, but they aren't going to pursue anything until it's published. So I better get to it. And I think it's got a lot of value. We're collaborating with people in Idaho, ARS lab in Idaho. They have some nitrogen trials. We're looking at it with colleagues in Minnesota. I have samples from Puerto Rico, and let's see, I have another set of samples. Anyway, they all of these have nitrogen or yield response trials to nitrogen application, and so that's what we're really interested in. I think the literature is abundant with these trials, and it would be unfortunate if people didn't share that information. But you know, I can understand they might not want to. But the beauty is that even from 1960, we could probably take an archive sample and run an analysis if they collected reasonably. So there's good potential, and the Soil Health Institute is certainly interested. They work with producers. They want to influence producers, and so there's real value. So that's all I have.